Unit Overview. In this unit, we explain a fundamental data structure called array. We shall examine distinguishing characteristics of arrays and look at the basic operations that are commonly performed on array data structure. The unit contains several illustrative examples to demonstrate the use of arrays. Visuals and interactive programs are also provided to reinforce the basic concepts. Objectives. After completing the unit, you should be able to learn basic concepts about array data structure, understand how arrays are stored in computer memory, know about the inserting, deleting, and traversing operations that can be performed on an array. Learn about the efficiency of basic operations. Explain the structure of multidimensional arrays and their usage. Understand the advantages and disadvantages of arrays. Introduction. An array is a collection of homogeneous, ordered, and finite set of elements. The homogeneous property implies that all of the elements of an array must be of the same type and structure. The simplest arrays normally consist of primitive data types such as integers, real numbers, characters, or Boolean values. More complex array structures might include strings and records consisting of several fields. The ordered property means that the elements of array are arranged in a sequence. Thus, each element of an array is identified by its relative position in the collection. For this reason, an array is called linear data structure. Another important characteristic of an array is the finiteness. By finite, we mean that each array can contain a fixed number of elements. In other words, an array data structure can hold specific number of elements. This number is called size or length of array. It is customary to depict arrays pictorially with elements arranged from left to right. Figure shows some typical representations of arrays comprising different data types. Observe that each array structure contains items of same type. A character array would consist solely of characters. It cannot contain integer or other types. Next figure shows examples of arrays containing composite or complex data types, namely strings and fixed length records. Recall that a record is a collection of fields which may be of different types. Notice that in the first example, all of strings are of same length consisting of 6 characters. If there are fewer alphabets, the extra places are padded with spaces shown as Bs. The second example represents an array of employee record. In order to preserve the homogeneity property, each record should have the same size and same composition of fields. For example, the name field cannot be 20 characters long in one record and of 30 characters in another record. Likewise, the salary field must be either integer type or floating type in all of the elements. Accessing array. Each array structure is identified by a unique name. The position of each element within the array is identified by a variable called index. The range of index is referred to as index set. For example, an array consisting of 10 elements would have an index set of integers varying from 1 to 10. Sometimes, the first element of array is counted as the 0th element. In this case, the index set would have range from 0 to 9. The smallest value of index is called lower bound and the largest value is called upper bound. Thus, the size of an array is given by the relation. The individual elements of an array are identified by the array name and array index. For this purpose, different notations are used. In the mathematical description of an array, the subscript notation is used. For example, the elements of array X consisting of n elements are denoted by the sequence. The programming languages, however, use bracket notation for array elements. The elements are defined by the array name followed by either parentheses or a pair of square brackets that enclose the index value. Fortran and Visual Basic use parenthesis notations such as C, C++, and Java use square bracket notation. Thus, elements of array X are denoted by. Sometimes, index is also referred to as subscript and index set as subscript variable. The contents of an array are often pictured using the name and index values. Figure shows an illustrative example of array X consisting of characters C, O, M, U, T, E, and R. Declaring array. Before an array structure is used in a program, it must be formally declared. This is required by the compiler in order to reserve necessary storage space for the array. The rules for array declaration differ with programming languages. In general, the declaration specifies array name, size, and data type. In C, C++, for example, this declaration means that the array X would consist of a maximum 100 data elements of integer type. Further, it is implicitly implied that the index set will have the range of 0 to 99. In other words, the array elements will be denoted by. In subsequent discussion, we will follow the C, C++ notation and rules for declaring arrays. Array storage structure. Storage structure represents the arrangement of data elements in the memory of a computer. An array is always stored in contiguous memory locations. The number of storage cells allocated to each element depends on the data types. Typically, a character occupies 1 byte, a short integer 2 bytes, and long integer 4 bytes. Figure shows the storage structure for an array mark consisting of short integers. In this storage map, the first element is stored at location 1000, second element at location 1002, and so forth. The numbers 1000, 1002 up to 1014 are referred to as storage addresses. The address of the first element is called base address. In this example, the base address of array mark is 1000. By knowing the base address, we can easily compute the addresses of other elements by using the general formula. Where address xj means storage address of the element xj, j being the index. Base address is the address of the first element x0 and size is the number of bytes allocated to an element. Thus, using the index we can easily compute the address and access the element without the need for searching other elements in the array. For this reason, the elements of an array are said to have direct access. Further, we do not have to keep track of addresses of all array elements. Only the base address is required to process other elements in the array. It would follow that storage structure for an array is quite efficient. It has, however, the drawback that memory allocated to an array is not released until the program execution is finished. Array operations. The basic operations on an array include retrieving an element, adding a new element to array, deleting an existing element, and inserting a new element. In addition, we can perform some auxiliary operation to determine the current status of the array or obtain some information about a specific element. These operations might include the following: checking if array is full, checking if array is empty, getting index of a specified element, and traversing to process array elements. Retrieving. Retrieving an element is the most common operation. It is also called accessing. To retrieve an element, we need to know the index value. For example, mark j would access the jth element of array mark. As noted before, the computer can directly retrieve an element without examining other elements in array. Thus, accessing operation is very fast. Further, since the access is independent of the number of elements in the array, access operation has a time efficiency O1. Adding. The add operation places a new element in the array in a position specified by the index. It is also called assignment operation. Thus, if we want to move an integer n in the jth element of array mark, we simply write mark j is equal to n. If the array already contains some element in the specified position, it is replaced by the new element. The add operation has time efficiency O1. Deleting. The delete operation removes an existing element from the array. In order to delete an element, say xj, we simply move all elements after xj one position to the left. In other words, elements xj plus 1, xj plus 2 up to xn minus 1, where n is the array size, are shifted to the left. Let us consider the process of deletion of an array element. The array shown initially contains letters P, Q, R, S, and T. In order to delete Q, the element R, S, and T that follow Q are shifted one position to the left. Notice that the deletion of Q does not release any memory space occupied by the array. The elements R, S, and T are simply reorganized. Inserting. The insertion operation adds a new element to the array in a specified position without replacing any of the existing elements. The position of the elements may be specified in terms of index value or relative to an existing element. The new element might, for example, be placed before a given element. In order to insert a new element in specified location, all elements to the right of element are being moved one place to create a room for the new element. For example, if a new element is to be inserted, it is placed before an element xj, then xj, xj plus 1 up to xn minus 1, and being the array size, are moved one position to the right. Let us consider an example to demonstrate the insertion process. The array shown contains letters P, Q, R, S, T initially. In order to insert an element Z before the element R, the elements R, S, and T that occur after R are moved one position to the right. The space created due to shifting of R and other elements is filled with the new element Z. Observe that after insertion of Z, the array size increases by 1. Also note that no additional memory space is allocated to accommodate the new element. Rather, the elements are simply rearranged within the memory block initially reserved for the array. Implementation of array operations. In order to implement the basic operations on array, we define a C++ class named array, which includes add, delete, insert, and other auxiliary functions. The structure of class interfaces is shown. Add appends a new element. Delete removes an existing element. Insert adds a new element in a given position. getIndex returns the index of a specified array element. isEmpty checks if array is empty and returns false or true. isFull checks if array is full and returns false or true. This method prints the contents of the array X. The detailed coding of all methods is given in the demonstration to follow. Array traversing. The traversal operation involves accessing and processing an array element exactly once. It is also called visiting. In order to traverse the array, we set up a loop with index varying from the lower to the upper bound. In each loop cycle, an element of array is accessed and processed according to the requirement. Some examples of traversing an array are finding the largest element, finding the smallest element, computing average of all elements, and printing contents of array. We now consider the implementation of these operations. Implementation of array traversing. A class for traversal of arrays is shown. It includes 4 methods to process an array of real numbers. Maximum determines the largest element in the array. Minimum finds the smallest element in the array. Average computes the average of all elements included. Display prints the array elements. The detailed coding of all methods is given in the demonstration. Performance of array operations. We have already seen that the time efficiency of access operation is O1. Let us examine the running time for deletion, insertion, and traversal operations. As discussed, in order to remove an element from the array, all elements to the right of the element being considered are shifted one position to the left. Thus, if the first element is deleted, there will be altogether n-1 shifts for an array of size n. Since shifting is the only major operation in deletion, we can conclude that the running time of deletion is On-1 or On in the worst case. If the last element is to be deleted, no shifting would be involved. Thus, best case has running time O1. The insertion operation is similar to the deletion operation, except that elements are shifted in the opposite direction. Thus, in worst case, the running time of insertion operation is On. To perform a traversal operation, we normally set up an iterative loop. In each loop, an element is accessed only once. Thus, altogether n accesses are made. As such, the time efficiency of traversal is On. There are no best or average cases, since all the elements need to be visited at least once. Two-dimensional array. Sometimes it is useful to group the elements of an array into smaller groups of equal size. Thus, each subgroup can be viewed as a smaller array within an array. This arrangement is referred to as two-dimensional array. For example, test scores of a group of students may be organized by student number and for each student by semester number. A two-dimensional array can be pictured as consisting of rows and columns. Figure shows such a representation for student scores by semesters. Formally, a two-dimensional array is a collection of homogeneous elements which are arranged into rows and columns. In order to identify individual elements, we need two index sets, one for the rows and other for the columns. The indexes follow the array name and are enclosed in a pair of square brackets. For example, if marks is a two-dimensional array, marks JK refers to the element is in jth row and kth column. In C, C++, the rows and columns are counted from 0. Thus, mark 00 would refer to the element in the first row and the first column. As with one-dimensional array, a two-dimensional array must be declared before it is actually processed. The declaration should specify the maximum number of rows and columns besides the array type and name. For example, in C++, the array portrayed in figure might be declared as storage structure for two-dimensional arrays. The elements in a two-dimensional array are stored in contiguous memory locations. Within the allocated memory, the elements may be stored row by row or column by column. The first arrangement is called row major and the second column major storage scheme. Figure shows a row major and column arrangements of an array consisting of 2 rows and 3 columns. If we know the address of the first element, we can compute the storage addresses of all the elements. For a row by row arrangement, the address of an element AJK consisting of n rows and m columns is given by the formula. In this formula, base address is the storage address of the first element A00 and size is the number of bytes allocated to an array element. It is assumed that both the indexes have 0 lower bounds. For column by columns arrangement, address formula is. These formulas are used by the compiler to locate and access an element of a two-dimensional array. Thus, all elements have direct access. This is the prime reason for time efficiency of multidimensional arrays compared to other types of data structures. String arrays. Two-dimensional arrays are useful in storing and processing of strings. A string is a sequence of characters which are normally stored in a one-dimensional array. In C, C++, a string includes a null as terminating character as shown in the figure. Notice that the last character in the array is null character. Thus, a string of size n is stored in a one-dimensional array of characters of size n plus 1. In several applications, such as text processing, we need to store a group of related strings. These could, for example, word in a text block or names of employees. Two-dimensional arrays provide a convenient and simple mechanism to store a set of strings. Figure shows a two-dimensional array which contains the names. This representation has the advantage that, apart from having access to the strings, we can also access individual characters in each string. Since in two-dimensional array, all rows must be of the same size, we need to allocate same number of columns for all strings, irrespective of their size. Thus, unless the strings are of fixed size, some of storage space may be wasted. Operation on strings. We can perform several operations on strings that are stored in an array. Some common useful operations are inserting new strings into array, deleting an existing string, searching for a string, sorting in specified order, and listing strings. The algorithms for string operations are same as those for a one-dimensional array. However, their implementations differ. In C, for example, strings cannot be assigned to variable. Instead, library functions are used for copying and comparing strings. For this purpose, the header file string.h needs to be included in the actual implementation. The interface class for string operations is shown in figure. It is designed to hold up to 20 strings, each with a maximum of 20 characters. The array is named X. It includes 3 common operations on strings. Add appends a string to the array. Del removes an existing string from the array. Insert adds a new string to array in a specified order. And disp prints the strings. Code skeleton for the basic class functions are given in the demonstration. Performance of two-dimensional array. A two-dimensional array allows direct access to any of the elements. Thus, accessing and assigning operations have a running time O1. For other operations such as inserting, deleting, and traversing, generally 2 nested loops are used. If the array consists of n rows and m columns, the loops would involve n into m cycle. Thus, the time efficiency for insert, delete, and traversal is O(n) into m. Matrix representation of arrays. A two-dimensional array of numbers is sometimes referred to as matrix. Matrices are frequently used in computer science and engineering disciplines. In graph theory, for example, matrices are used to represent links between nodes. Image processing application stores pixel values in rows and columns for different kinds of transformations. In mathematics, matrices are frequently used to solve a set of algebraic equations. Matrices are commonly used in quantum mechanics to compute energy spectra. In engineering applications, matrices are frequently employed for structural analysis. In mathematics, the subscript notation is used for the matrix element. Further, the elements of a matrix are enclosed in a pair of large brackets. Figure shows a pictorial representation of a matrix consisting of n rows and m columns. It is called n by m matrix. A matrix with the same number of rows and columns is called square matrix. The elements of a matrix with the same subscripts are referred to as diagonal elements. Thus, A11, A22 up to ANN are the diagonal elements of an n into n matrix. A matrix is called symmetric matrix if the corresponding elements below and above the diagonal elements are identical. Thus, in a symmetric matrix, Aij is equal to Aj for all j and I. Distance between several cities, for example, can be represented as a symmetric matrix. In some applications, matrices contain only a small number of non-zero values. Such matrices are known as sparse. A special form of a sparse matrix is called tridiagonal, in which all elements above the main diagonal are 0. The elements of a tridiagonal matrix can be stored in one-dimensional array. Figure shows an example and the correspondent array. Notice that the matrix with 16 elements is stored in an array of 10 elements. It can be shown that in general an n by n tridiagonal matrix can be stored into one-dimensional array of size n, n-1 by 2. In this way, a large economy of storage space can be achieved. Matrix operations. Common operations on matrices are addition and multiplication. The sum of pair of matrices is obtained by adding correspondent elements. Thus, if A and B are two matrices having same number of rows and columns, their sum C is given by for all values of indexes I and j. Matrix multiplication is somewhat more involved. The product of a pair of matrices is obtained by multiplying all elements in the correspondent column of first matrix with all elements in the corresponding row of the second matrix and adding together products of elements. If C is the product of matrix A and B, the elements of C are given, assuming that both A and B are n by n matrices. In mathematical notation, the expression can be simply written as where I and j vary from m to n. The symbol sigma represents sum over the index k, which varies from 1 to n. Three-dimensional array. A three-dimensional array is a collection of homogeneous ordered data elements which are accessed using three index sets. The indexes are enclosed in three pairs of brackets which are preceded by the array name. Each index set has its lower and upper bounds. In C++, the lower bound is 0. The three-dimensional array extends the notion of grouping of elements at three levels. For example, student scores might be grouped by student numbers, semesters, and subjects. The first index would refer to the student number, second to semester number, and third to subject number. Figure shows a pictorial representation of a three-dimensional array score. Notice that the array is split into 4 tables for the convenience of pictorial representation. Inside the computer, all of the elements are stored sequentially in contiguous storage location. The elements of a three-dimensional matrix are described in terms of rows, columns, and planes. The array M of test scores consists of 4 rows, 3 columns, and 4 planes, which refer to student number, subject, and semester. For example, M 0, 2, 3 represents the score of the first student in third subject in fourth semester. Advantages of array. Major advantages associated with the array data structure are: Number 1. It is possible to use a single variable for handling a large set of homogeneous data. Number 2. Arrays provide direct access to any of the data items. Thus, storage and retrieval of information are both fast and flexible. Number 3. It is easy to construct and use arrays. Almost all programming languages support creation and initialization of array with the help of simple declarative statements. Number 4. Arrays are indispensable in implementing iterative algorithms. It is easy to set up loops by taking advantages of array index sets. Number 5. Multidimensional arrays facilitate grouping of homogeneous data items into hierarchical structure. Limitations of array. Arrays have certain limitations as well. Their main disadvantages are: Number 1. array size cannot be increased or decreased during runtime. Thus, arrays are not useful for applications which use large data set of unpredictable size. Number 2. Variable length strings cannot be efficiently stored into arrays because large amount of storage space will be wasted on account of padding space characters. Number 3. Insertion and deletion operations on arrays are not efficient. Every time some data item is added or removed, a large number of elements may need to be shifted. Number 4. Normally, arrays are allocated memory blocks out of the program space. For very large data sets, the program may run out of the storage space. Number 5. Some of the programming languages, such as C, C++, do not perform range check on array indexes. If an index has trespasses the upper or lower bound, incorrect data may be accessed or stored in wrong location. Some of the deficiencies of array are overcome in other data structures, which we will study in subsequent units.